All right, section 2.9. Today we're going to take a look at complex numbers, not to be confused with complex fractions, which is what we did last time. And to start with, we're going to encounter what's called an imaginary number. So imaginary numbers hinge upon the imaginary unit I. The imaginary unit I is defined as I squared is equal to -1, or I is equal to the square root of -1. So early on in the semester, there were some places where we had some square roots of negative numbers, and we were working in the real number system, and so at that moment we said that doesn't exist, and that's true. In the real numbers, the answer didn't exist. Now we're going to work in this situation or in the context where we've got a broader definition of numbers, and they do exist. You might also remember that at one point we defined this picture, and it looked something like this, where we had all the real numbers in here, right? We had the rational ones and the irrational ones, and we broke them down into little squares in the middle. It was like the first or second day of class. Well, there's a broader number system. What actually happens is that if I go like this, I actually have what are called the complex numbers. That's what we're working in now. And in the complex numbers, we have the rational and the real and all the things we've had before, but we have some additional things. Namely, we have I, and we have I to the fifth and things like that, and we have I plus 2 and those kind of combinations of things. The interesting thing and the nice thing about the unit I is that it acts in many cases a lot like just the variable x would act. And so when we get to problems like 5 and 6 here, you're going to feel like, I already know how to do this. It's just algebra. Like, it's just combining like terms, and it does feel that way. Before we get to that, we're going to take a look at simplifying negatives underneath radicals. So if you have a negative underneath the radical, the negative will come out of the radical. You can think of it that way anyway, as the number I. This 5 still doesn't have a pair underneath the radical, so it's still 5 underneath the radical. And there's nothing to show, it's just a rewriting piece. So 2 is a little different. The I will come out, but do you remember what we have to do with the number 8 when we're underneath a radical?
Break it down.
We have to break it down. And we've broken things down multiple ways, but one of the ways that we've looked at is taking a look at this is 2 times 2 times 2. So since it's a square root, which we're only working with square roots in this section, by the way, there's no cube roots or anything. Square root, how many numbers have to be present in order for us to pull one out? 2. So I'm looking for a pair of numbers. I do have a pair of 2s, so the I will come out. The 2 will come out as well. Technically, you could put the I and then the 2. More commonly, you'll see people put the number before the variable. It's not a variable, but the letter-looking component. And then what's left underneath my radical? 2. So this is 2i square root of 2. And somewhere on there show that you've broken down the number 8. So this one's interesting because what you see happening here is you see the multiplication of 2 imaginary values. We're going to deal with each of them individually first. Actually, I think we're going to deal with them like this. We're going to deal with the negatives first. Let's do that. So there's an I that comes out and it's square root of 3. And then there's another I that comes out and it's square root of 12. Okay, that okay so far? We're going to deal with the 3 and the 12 separate. But I can multiply the I, and that gets me I squared. So far, so good? We had a property of radicals that says that we can actually put the radical pieces, if it's multiplied, all underneath together. So I have a 3 underneath here, and then I have the number 12. Instead of writing the number 12, let's actually break 12 down. How will 12 break down?
3 times 4.
3 times 4, and 4 is? 2 times 2. So I have a 3 and I have a couple of 2s. This isn't the only way to see this one, but it's one of the ways that works nicely for other options. You're right, I have 2 pairs. I have a pair of 2s and a pair of 3s. So a 2 comes out and a 3 comes out, and 2 times 3 is? 6. Now, if you were dealing with variables, this would say something like 6x squared, and you would be done and you would be fine. The problem is that I squared has another form. What does I squared equal? Negative 1. Yeah, negative 1. It's the definition we had over here. I squared equals negative 1. So anytime we get I squared, we have to replace the I squared with negative 1. I'll write it in here like this, but you certainly could just move to the fact that it's -6. On this one, it also would have been equally nice to simply multiply the 3 and the 12. What is 3 times 12?
3 times 12, 36.
36. What's the square root of 36?
6.
6. It would have been nice here just because it's a perfect square that results. That doesn't always happen. So that's why I broke it down instead of just multiplying it out.
Why couldn't we break down like the 12 in the very beginning?
You could. If you did, you would have ended up with a 2i square root of 3 at this point. There's just a different ordering. There's nothing wrong with that. So if you had broken it down at the beginning, you would have started out with the stuff that looked like this. And you would have done the same things. You would have had the I squared, the 2 would have been in front, the square root of 3, and the square root of 3 would have been 3. All the pieces would have been there. They just would have been done in a different order. So they don't have to be done in the order I did them in. Yeah. All right, how about number 4? Well, we have a square root of -20 and we have a square root of -2. So I need the i's to come out, and I do that first. So here's times square root of 20. And Greg, you could do that here too, right? Like you could simplify the square root of 20. But I'm actually not going to on purpose because it simplifies nicer if I wait. But if you had, it wouldn't be wrong. It would just be done in a different way. And this is I square root of 2. Everybody good with that so far? What's going to happen to my i's?
Square.
Well, they're gonna cancel because they're divided. They aren't multiplied. If they were multiplied, they'd become squared. Here they're divided. Just any number divided by itself, at least not 0, is equal to 1. So the i's are going to cancel. We have a property of radicals that says that if I have division of radicals, I can do the division inside first and then do the radical. So what's 20 divided by 2?
10.
10. And we get to the square root of 10, which we're done. If we had worked ever so hard to try to simplify the 20, I would have then had to rationalize the denominator. It would have been actually quite a bit more work on this one. There's no guarantee on which way is going to be faster, but this one works really nice like this. Okay, 5 and 6, which is the ones I was wanting to get to show you that it works just like algebra. All right, so I have the addition of 2 imaginary values. And so or complex numbers specifically. So as I'm adding these complex numbers together, I add the parts that are like. So what are 2 like terms that you see?
3i, 2i.
Okay, -3i and positive 2i. What does that equal?
Negative I.
-I. And it just so happens on this one that the other 2 terms are also like terms. I have real numbers, 2 and 6, and 2 plus 6 is
8.
8. 8 minus I. Feels like just with an x's, right? Just like. What do you notice has to happen on number 6?
Needs to be in front.
Okay. Yeah, so there's a negative here, and I'm going to distribute the negative through, right? So whether you have to actually see it, I like to see it personally, or whether you want to do it as subtraction, that's okay too. If you rewrite it by distributing the negative, the problem looks now just like problem number 5 looked. So it's kind of friendly that you turn it into something you already know what to do with. -4 and -6 are like terms. You add them together and you get what? -10. And then the 2i and the 6i are like terms. Added together you get? Ooh. Careful on your signs. The negative distributed, so the -6i at the end is now a positive 6i.
Oh.
So instead I have 8i. Yeah. Signs is a good thing to, well, it's not a good thing, but it is something that trips people up on these. Just be careful with your signs as you're working through. Okay, is that good for 5 and 6?
Yes.
Addition and subtraction feels a lot like just using x's. Multiplication, that's 7 and 8. Multiplication does too, but it's got a caveat at the end that we have to be sort of aware of. So to start with, it looks just like what it did before. We distribute here because I have a factor in front and I have a binomial in the middle. I can distribute the 5i. So what is 5? What do you think 5i times 2 should be? Well, it should be 10i, of course. What should 5i times 3i be?
15.
Okay, so first let me write down as positive 15 what?
I squared.
I squared. Okay, but I squared is
Negative 1.
-1. That's the caveat at the end that we have to be careful of. So when I multiply I squared, I end up multiplying it times -1. Let me take one more step just to make sure everybody's seeing where it's coming from. You don't have to write that step in. It just changes the sign. So 10i minus 15. Okay? Number 8. Well, number 8's a binomial times a binomial, so we FOIL, right? So we do our first terms. 3 times 2 is 6. Outer terms, 2 times -I is? Yeah, -2i, yeah. My inner terms, 2i times 3. 6i. And then my last terms, 2i times -I. -2i squared. Okay, so at that point, we're going to combine like terms and simplify the I squared. We can do that all in the same step pretty nicely. The 6 at the beginning will stay a 6 for the moment. I have -2i and positive 6i. 4i. And then what happens at the end when I have the -2i squared? It becomes a positive 2. Right? The I squared is -1. And therefore it changes the sign on the 2 to make it a positive 2. And then we can do what? Yeah, we got another set of terms to combine. So we've got 8 plus 4i. Okay, so they're coming in pairs. We did 2 multiplications, so our last thing to do is 2 divisions. Division's a little bit different. So the division actually feels like what we did when we did division with radicals, and that should kind of seem right because I is a square root of -1, right? So when you see division, what I want you to remember is that division really means rationalizing denominators. Now, when we had rationalizing denominators before, it meant no radicals on bottom. But I is a radical, right? We don't see it present when we were looking at I, but it is. So what this means is that I will have no i's on bottom. That's my goal. Okay, so we have seen rationalizing denominators. We've also seen what we're about to do in another fashion when we talked about differences of squares. Do you remember doing differences of squares with factoring? Nobody wants to admit they remember. That's scary.
What?
Do you remember doing differences of squares with factoring? So differences of squares had things that looked like this. A squared minus b squared.
Oh, yeah.
And it had this nice factoring a minus b and a plus b. So a minus b and a plus b are called conjugate pairs. They're conjugates of one another, okay? So they're the same values, just the opposite sign in the middle. This idea right here allows us to eliminate middle terms, right? I don't have an inner and an outer term because the inner and the outer terms are the same and they add to 0. One's positive, one's negative, so they add to 0. Why does it matter? Well, because over here, when I have the 3 plus I in the denominator, I need the conjugate in order to get rid of the I. So let's take a look. Yep, 3 minus I would be my conjugate. Whatever I do to the bottom, I have to do to the top. Let's do the bottom first, just so you can see why we want to do that. So because it's a conjugate pair, or because you can actually multiply these and eliminate the middle terms, right? One's positive 3i and the other one's negative 3i. Because of those things, I end up getting only the first 2 terms multiplied. 3 times 3, which is 9. And I get the last 2 pieces multiplied. What is I times negative I?
Nothing.
It's not nothing.
Nothing. It's 1.
It's 1. It's negative I squared. I squared, right? So I times I is I squared. One's positive, one's negative, so it's negative I squared. You might say, well, but I still have an I. But you don't really. Because what's I squared? 1. So this denominator is actually now 9 plus 1, which will become the number 10. So I realize I've written a lot of steps and I've ignored my numerator for a moment, but This is why we want conjugates to be used, is because the inner and outer terms cancel, and my I squared will become a -1, and I will no longer have any i's. Okay? The numerator typically will still have i's involved, right? That's what we're going to expect to have happen. On the first one here, we're going to just distribute this through. So 2i times 3 would be 6i. And then 2i times -i would be -2i squared. Is that okay with everyone?
Yep.
Okay, so the 6i stays. But what happens when I have, that's not an i. Let's try that again. 61 stays, no. 6i stays. What happens to the I squared then?
It becomes a negative, or -2 times -1.
So we get
Yeah.
+2, right?
Yep.
So the -2i squared becomes +2 at the end. I can't combine those terms, so it really will just stay 6i and 2. But there is one more thing at the end that I can do on this particular problem.
Divide them all by 2 over 2.
Yeah, all three of my terms, remember terms are separated with addition and subtraction. So all three of these terms are divisible by 2, so I can reduce them or divide them all by 2. So this is the 3, this is a 1, and this is a 5. So the end result I end up getting is 3i plus 1 over 5. Notice on number 10, I'm not going to start the problem just right away, just hold tight for me. If number 10 were an answer for something, there's actually 4 components, right? There's 4 terms. Do you guys see all 4 terms? Okay, and they're not all even. So you have to have all the terms even if you're going to do some sort of a division like we just did, and this one doesn't start that way, just an awareness factor here. So my goal is to get rid of the I in the denominator. How do I do that?
Multiply by the opposite of itself.
Okay, so what would that be, Gregory?
-4 minus 2i.
Close?
Or 4 minus 2.
There you go. So it's only the sign in between that's different. So I have 4 minus 2i. And when I use the conjugate, I will only get the first 2 terms multiplied. So 4 times 4 is 16. And the last 2 terms multiplied. What is 2i times -2i?
4i squared, or -4i squared.
Yep, -4i squared. Okay, we'll finish our numerator now. We'll come back. We'll keep going to the denominator in a minute. But my numerator, I actually have to FOIL this time. And so it's actually going to be uglier than the denominator because I don't have conjugate pairs. So my first 2 terms, 2 times 4 gives me 8. My outside terms, 2 times -2i gives me -4i. My inside terms, which is -i and 4, gives me, another -4i. And then my last 2 terms multiplied, -i and -2i.
Plus 2i
Positive 2i
squared.
squared. Okay, numerator's messier than denominator, agreed? Sure. Okay, the denominator simplifies nicely. It's 16, and then what happens to the -4i squared?
Becomes a plus 4.
Yep, positive 4. The top has some pieces that combine now as well. The 4 i's do, right? So I have 8 at the beginning, and then I have minus 8i. And then at the end, what's going to happen to my 2i squared?
Becomes a -2.
Becomes a -2. Just -2. Yeah. Okay, so combining that 8 and the 2 gives me a 6. So I have 6 minus 8i on top. What's on bottom?
64.
It's not multiplied.
Oh, I'm bad.
20. It's added, yeah. So I have 20. The pieces on bottom are going to be added together. And what do you notice?
Oh, you can divide them all.
You can divide them all again. They don't always work that way. These just have. So dividing each one of them by 2, I have a 3, a 4, and a 10. So I have a 3 minus 4i over 10. okay? It's gonna feel like it's just a lot of things we've done before, with the exception that I squared equals -1.